All right, so I've got, for my time, it's 10:40 p.m. on Tuesday evening. That's one of the interesting parts about presenting virtually is, speakers coming from all over the world to present at this. So welcome, thank you for having me, everybody. So tonight, or for today, for you all, we'll be talking about graph databases and using them within Cosmos. Sure enough, just a quick little history about me and graph databases and such. So about 6 years ago, 5 or 6 years ago, I was actually working on a database system that was a complete mess. I inherited this absolutely atrocious database. To show you how bad this thing was, we had one table that had just shy of 1,400 columns on it. And if you had asked me before I joined the company, how many columns can a SQL Server database have, I would have never told you 1,400, right? And I do know for a fact it's 2,048, because I actually also did the math of how long it was going to take for us to run out of columns, because we actually had code in the application that would create columns into this table. So that was part of the reason why it had grown so much. And so we were looking at solutions for this, and basically one person said, well, you need to really look at NoSQL databases. And I was like, I'm not so crazy about NoSQL database for, and some of it was just because I didn't really know enough about it. But being a Microsoft person and really enjoying Microsoft, products, I looked at what was in Azure, and sure enough, you had Cosmos. And then one of the things that Cosmos was able to do was graph databases. And so ever since then, I've just, because it was a perfect solution for what we needed. And I've always really enjoyed working with graph databases. Now, the one thing, the caveat I put up always up front is graph databases are awesome, but they're not necessarily the replacement for everything, right? I mean, they don't solve all the problems. All right. Not focused on my slides. There we go. All right. So sure enough, my name is Chad Green. I'm I'm Director of Software Development at a company called ScholarX here in the United States. We basically do online medical learning platforms. And then there is all my contact information. So sure enough, feel free, if afterwards you have questions about Azure, Cosmos, Gremlin, and so forth, definitely feel free to reach out to any of these different contact means. All right, so what I want to start off with is talking about, what are graph databases? What are we talking about? What are we looking at? And I usually like to start with the mathematics behind this, because it is all based upon mathematics. And sure enough, according to math, graphs are one set of areas of concentration in discrete mathematics. For those who are not mathematicians, we're talking about the study of mathematical structures that are fundamentally discrete rather than continuous, right? And so by definition, and that's what we see here, a graph is a structure amounting to a set of objects in which some pairs of objects are in some sense related. These objects correspond to mathematical abstractions called vertices, and the related pairs of the vertices are called the edges. And sure enough, generally we see a graph depicted like here, right? So the circles or the dots are your objects, right? And according to the math theories, they're called vertices. And then you have the lines, and generally they are curved lines. But those are showing the relationships. And right away, we can start seeing why there's some benefit here, right? Because I can right away, I can see that 4 has some type of relationship to 6, 5, and 3. I don't have to look at any data or anything like that. I can right away visually see those kind of differences. And that's part of the reason why graphs have some real good power in here. If we look at the formula of graphs, basically we're talking about it's an order pair using the equation G equals VE, where V is a set of vertices, E is a set of edges that which are unordered pairs of vertices, and and basically it creates those pairs of that. So real quickly about the history of graph theory, because actually it's pretty darn interesting. And actually our story starts in this small little town, well, not that small, but of Königsberg, Persia. So Königsberg was founded, as people were coming back from the Crusades, and basically, it became a very prosperous trading town. And on Sundays, people like walking around the town and viewing all the great sights. because again, they had a lot of money, and so the city was actually built up very well. And the interesting part was you had of the city, you had the Prego River running through. And because of this, they actually created these 7 bridges. I mean, it's funny, actually, these 7 bridges are not still around because of the world wars. But at one point, there were these 7 bridges. And one of the things that the townspeople would like to do was they would actually try to play a game of crossing all 7 bridges, but only crossing them once. And no one can figure out how to do it. And sure enough, I mean, looking at the map, you can kind of see there is no way, right? You're eventually going to have to cross a bridge a second time. And this kind of perplexed the people of Königsberg. Now, luckily for them, nearby, you had Leonhard Euler. And Leonhard Euler, this guy was an extremely prolific mathematician. He published more than 500 books and papers during his lifetime. In 1775 alone, he averaged a mathematical paper per week. And on top of it, he didn't just write about math, but he also wrote about mechanics, optics, astronomy, navigation, hydrodynamics, and so forth. Right? Remember, he's so well respected that at one point he was on the 10 Swiss franc bill. Well, at any rate, so the mayor of Königsberg actually sends, I almost said an email. That would have been kind of funny, but actually sends a letter to Euler, saying, "Hey, can you help us solve this problem? We want to know why we can't do this." And the funny part was he originally said, "This is a waste of my time. Why you bother me?" Right? But he was thinking about this some more, and more importantly, he was thinking about some conversations he was having with some people who were doing some new stuff with geometry, and it really got him interested. And so he actually researched it and did some thinking about this. In the end, he came up with this paper here, and I'm not even going to try to pronounce the original language, but the solution of a problem relating to the geometry of position. Right? And this paper not only solved the 7 bridges of Königsberg problem, but for any number of points. Right? And this is actually considered to be the history, or I'm sorry, the beginnings of graph theory, right? Because this is what kind of gets graph theory started. And sure enough, if we look through the rest of history, there's a lot of interesting stuff. I won't talk, directly about all these gentlemen in here, but we have solving the knight problem. So the whole idea of finding the sequence of moves a knight on a chessboard so it moves, it hits every square once, right? And while that seems very trivial, there's actually a hard problem to solve, right? And graph theory was able to help that out. It also had a lot of work in topography, right? Was solved in this. And sure enough, as you see through on here, we have more and more people that were involved, all this type of stuff. All right, so sure enough, if we were to look at some applications of graph theory itself, it's actually used quite a bit. Number one is linguistics, right? Graph theory gets used for matching words and meanings of words, right? To help figure out, how words relate to each other and so forth. Physics geometry will use it a lot for the study of molecules. Social science is actually one of the biggest uses of graph theory outside of mathematics, and they use it to measure an actor's prestige or to explore rumor spreading. Biology is actually a really interesting use case. They'll use it a lot for tracking the migration patterns of animals and actually watching the diseases and the different patterns that happen because of these. And then, obviously computer science. That's why we're here today, right? Is, because we use this for graphing out data, to include, representing networks of communications, data organization, computational devices, and so forth. But sure enough, I've been in software for a long time, and I was always promised no real math. So that's enough of all the math, all right? Let's talk about what graphs mean when we talk about data. And the big thing is that it allows us to model all kinds of scenarios more naturally, right? It actually, represents the entities as vertices and the ways in which those entities relate to the world as relationships. Think about it, when we look at a relational database, it's funny, relational, but we're end up having to do foreign keys, or we're having to do join tables, right? In graphs, we don't have this, right? Because the data is directly related. If we're looking at an example of a data graph, and here we kind of see Twitter followings, right? So Chad Green follows and is followed back by Azure Cosmos. Azure Cosmos follows and follows back El Bosque. But you notice that Chad Green follows El Bosque, but not the other way around. And actually, I need to change this because he actually does now follow me. But the point being is, again, right away in this visualization, we see the data. We can see the way how the data flows. So when we talk about what a graph database is, we're talking about a database that's using this graph theory mathematics to have graph structures that represent and store data. And more importantly, it doesn't try to change them as you need to define them. All right, but more importantly, when we're really talking about graph databases and how they use graphs, we're really talking about a property graph, right? And this is a mathematical term, but this is also what is being used in graph databases. And what do we mean by this? Well, so we have those nodes, those vertices, and those relationships, or the edges. And then those nodes and relationships contain properties. And they can, a node or a vertex contain one or more properties, and but also your relationships can have 0 or more properties, which is really, really nice. And then the relationships are named and they're directed with a start and end node. And so here we see an example. We see this object here, Chad Green, Louisville, Kentucky, Director of Software Development. And then that object is labeled, right? So it actually defines what this object is. So this object is an employee with those properties. Over here, we see this company object with ScholarX, location, Elizabethtown, Kentucky, right? And then we have the relationship, works for, and then we can also have the date of employment, right? So, I mean, that's a more logical place to have that type of field, especially maybe that person, works there multiple times. We can actually have multiple relationships in there. So what is the power? I mean, other than, what we saw with the fact of being able to relate data graphically, and we'll see this even more as we get further in our demonstrations. But there are some 3 key tenets that make graph databases extremely powerful. One is performance. This is one of the more compelling reasons to look at graph databases, because no matter how much data I add to it, the performance will remain relatively stable. Unlike most other database systems, once I keep on adding more and more data to it, right, I get to bottlenecks, and I'll eventually will slow it down. I mean, grant you, we can do some really interesting stuff with indexes and so forth, and partitioning of data. In here, graph databases don't have those problems, and the reason is because the way how we're searching for data, we're actually searching for a subset of data. Because I'm not having to go over across a larger set of data. I'm generally able to return my data again in the same speed. Next is flexibility. Because a lot of it's because of the fact it's in the SQL database. But I have lots of flexibility. I can structure my data as it works correctly. But also, as the problem space evolves, we can have the data evolve with it. And we're not having to do, expensive and hard to do, data migrations. I'll be walking through some demonstrations here in a moment, and you'll see that even more so. And then finally, and it kind of goes along with this, is agility. Right? I can quickly move my data. I can make these changes without having to do lots of staging work and so forth. So if we look at some common use cases, here's a big list of them. I want to highlight a couple of these. Number one, actually the biggest use of graph databases in computer science is social networks. So Facebook, Twitter, LinkedIn, they're all based off of graph databases. That's the way how that they can actually do those relationships. Recommendation engines. So you go out to Amazon, you purchase something, and then a day or two later, you get an email saying, hey, you probably also would be interested in buying this. That's actually happening through a graph database. It's looking at those relationships and making those recommendations. Something that gets used a lot is communication networks. And this actually, when you think about it, makes a lot of sense, right? Because normally what we do with communication networks, we'll draw out a graph that defines things, right? You know, and I can do this with data. And the nice part about doing this with a graph database is when when a node goes down, I know all the related nodes that are affected, and then all those nodes they're related, and so on, right? Fraud detection. This is one of the newer areas that's starting to use graph databases quite a bit. And think about it, fraud detection. What are we looking for? We're looking for patterns. And you know how we're searching a graph database? It's through patterns, right? So, fraud detection works really well for here. Search. This actually gets used quite a bit. I can't find recent documentation, but at least at one point, Google was running on a graph database, their own graph database. But a lot of other databases actually use, a lot of other search engines use graph databases. And the final area to point out, and this is definitely one of the more newer ones, but identity and access management. And the big one, I mean, if you heard of the Microsoft graph, right? Where Microsoft, you have complete access to the user authentications, but also, the roles they have, the documents they have, the computers they have, and so forth, right? That is the reason for that name, Microsoft Graph, is because it's a graph database. Now, interesting enough, because I get this question, especially once I get a little bit further down this talk, Microsoft Graph is not using Gremlin within Cosmos, which is kind of interesting. All right. So now I've talked a little bit about graph databases. Let's look at a graph versus relational, because I mean this is the most obvious. Probably most everyone here, you've done plenty of relational databases. You're kind of interested in what could I do with this graph data. So let's start off with a simple side-by-side comparison. First off, in relational databases, we have tables. Sort of the related item is vertices, although really a vertex would be more akin to a record or a row within that table, right? Because a vertice is an individual item, right? So you can kind of think with that label, though, we get that relationship to the tables. In a relational database, we have a schema and we have nullable types, right? A graph database is no schema, right? Honestly, a lot of times when I hear NoSQL, I always think a better name is no schema, right? Because actually a lot of times we're creating NoSQL databases with a SQL language. But sure enough, there is no schema, right? I'm not worried about that. Now, the one thing I always hear, especially from database people, well, if there's no schema, how are we supposed to manage, ensure that data integrity and everything? Basically, instead of the database managing that, is really up to the applications. Right, and which means you need to have strong development teams, that are well disciplined and well matured. Next one, in a relational database, again, the funny part is relationships are not a first-class citizen, right? You actually have to do it with foreign keys or join tables, right? Whereas in a graph database, relation is a first-class citizen. And the one thing that a lot of people don't even realize, the relational database was actually designed after accounting ledgers, right? There's a reason why, like when you look at a database, when you look at the data, it looks very much like Excel does, right? The whole idea of that. Of course, if you're the British healthcare, apparently use Excel anyways for your databases, but that's not unique to the British healthcare also. But all right, final area, in the relational database, we're getting related data with joins, all right, and sometimes multiple joins. Whereas on the graph database, it's through a pattern, right? And we'll see this. We'll actually see some of those languages, or some of the language, how we actually retrieve data in a pattern. So sure enough, I promise there's going to be some demos. Now the fun part is I actually will never leave slides because I just put everything in here. But what we're going to do is we're going to walk through a set of data, right? And we're going to see how the data can be written in a SQL or in a relational database as opposed to how it would be written in a graph database. And this is a very simple database, just a couple of tables get created in here. But the idea here is to get to see the differences. So I could say, so sure enough, we'll start off with a human resource database, right? Just some general information, right? And we can see this, we have this table, employee ID, employee name, employee group. So a very simple table. Honestly, there's some things that, if, anyone who's been doing databases for a little while, say, well, you should make this change, you should make that change. But that's okay. Again, we're purposely keeping this a little bit simpler. Now on the graph database, I'm sorry, not on the graph database. And in here I have the SQL. Right here, I'm showing the SQL how we do this. Right, so very simple. I create the table, with my primary key, and then populate the table. Right, so very simple. All right. So now on a graph database, this is the way how we're going to do this. And let me know, a little secret. This is the most Gremlin you'll see on one screen. All right. So in here, in the first part, we're creating those group nodes. Now everything in Gremlin starts with a G dot. So I'm going to say G dot add V, so add vertex, and in that group, that's the label. So add a vertex with a label of group, and then I give it the property. Right, so property ID sales, right? Property ID engineering, and then you can see we're adding those employees, very similar way. And then, sure enough, if I was to have multiple, right? Maybe we have the ID, but then maybe we have given name and surname, right? We would just do another dot property, given name, Willis. Sorry, I had to think about the British terms. Of course, in America, that's first name, but and then but then dot property, surname, Hawkins, right? So we can see that. And at the bottom, here's where we see where we're creating those relationships, and you start seeing patterns, right? So here we actually start with a search, right? So again, I'll start with my G dot and then V, so give me the vertices, and then give me the vertices. When I put it in the parentheses right away, it basically tells me give the vertice with that identifier. So in here, the identifier of sales, and then I'm going to add an edge of member, so that's the label of that edge, and then 2, and then go find the vertice that has the ID of Willis B. Hawkins, Neil S. Vega, and then Ada, right? And so that's the way how we'll create the data. So sure enough, if we were to look at this, let me just get out the screen. In the relational database, we have that one table. Again, not that hard to understand the data, but in the graph database, right away, we're starting to see relationships. We see how Neil and Willis, how they tie to sales. We see how Ada ties to engineering. It's visual, right? So we see it right away. And sure enough, and this does trip people. So, obviously in the SQL database, there's 3 rows, 3 columns. In the graph database, we actually have 8 documents. Here, let me move over this side. And we have 8 documents over there, right? And sure enough, everyone's always like, oh, you got a mistake in there. No, because those relationships, those edges are documents themselves, right? Because again, they're first-class citizens. They actually are part of the whole document structure. And here we can start seeing the queries, select star from employees, very simple. On here, GV, and then because I put nothing in parentheses, so give me everything, all right? But then filter that where it has a label of employee, right? So that will just give me all of the objects that have that label. All right. Now, of course, that's all great, easy to see, but data continues to grow, right? Company reorganizations happen all the time, right? We'll see we need to reorganize the company for some strategical reason, right? And in this example, we're going to say that now an employee can belong to multiple groups, right? And in our example, Ada engineer is now also going to work with the with the sales department, right? So probably like a sales engineer type role. So again, now if we see the SQL, we're going to create a groups table. Pretty simple. Now, grant you, full caveat. I would have done this at the very beginning, but that would have kind of busted some of the simple demo. And then we're going to create these join tables, right? And I wasn't very original with my table names. Some of these will get even better, but so employee group, group ID, employee ID, and I have my foreign keys relating everything together. Well, I'll populate everything with an insert query to migrate the data. And then because we want to make sure we keep our database clean, we'll drop that employee group column because we do not need that anymore. In the end, we get this, right? So 3 tables, I mean, not that hard to understand, not that hard to explain to an executive, right? But also not, I mean, it's starting to get a little bit more complex, especially when I look at the join table, right? 1, 2, 3, 3, 1, 2, right? I mean, those mean nothing to a human, right? Now, the funny part is, as we get more used to our database, we know what those mean, right? A lot of times. But I mean, normal people don't understand what those numbers mean, right? And that's where we start seeing the problem. So you saw what we had to do on a relational database, and it all made sense. On a graph database, all I had to do was just add this one link, right? Because that's all that happened. In the end, that's all we did differently. I didn't need to make any structure changes. I just needed to say, give me the sales, add an edge of member, and then add that to Ada. And now, we see this, right? So, on the relational side, we added these tables, these rows, and then these 4 new columns and removed a column. Whereas on the graph database, excuse me, I had to get a quick drink of water. On the graph database, we just added that one document, the member relationship. That's all we had to do. And sure enough, if we look at the queries, now we start seeing joins being added in, right? And sure enough, in this example, I did 2 joins. Again, not that hard to write. I mean, this is all makes pretty good sense to us. But on the graph database, I just did a pattern, right? So give me sales, and then give me the out edge, right, of member, and then go back and give me the inbound vertices. Now, sure enough, it's interesting. If I don't have that last part, the NV, I actually get the edges, right? So it's kind of interesting there. And I will say, you see these ins and outs. We'll show some even deeper code here in a couple minutes. And when you get to those, you definitely want to understand your ins and outs. So you want a good documentation there. All right, but of course, data continues to grow. Corporate mergers. It's kind of funny. I worked for a company. I ended up working for 7 different company names in like a 3-year time span, but yet I had 1 employee ID, right? All because of mergers and splits and so forth. I mean, these happen all the time. And now in this example, we're now going to have a nested group, so that groups can belong to other groups. And I made just a very simple example. I just call it a product group. But here it's easy. I just need to create a group in there. But I now need I now need to associate everyone, because basically in this example, everyone that just is going to move into that product group along with the groups they are belonging to. But then I need to create that join table, right? Because that's the only way to actually, even inside of a table, to relate an object to another object. Unless you had a parent, right? I mean, if it was just simple parent-child, then we wouldn't have to necessarily do a join table. But in this example, we're allowing them to be parts of multiples. And here you can see we're doing the SQL to get the data in there. Now, look, now we're starting to see where this data is getting more and more complicated. All right, this is getting harder to show to an executive to explain what differences we're making. And while it might sound like, well, Chad, why are you talking so much about talking to executives? Because what I've learned over 30 years of software development is we end up talking to executives more about data than we want to. And one of the hardest things we have to do is explain this stuff. Now, granted, it's not the only reason why we want to do graph databases, because even just trying to explain this to a data analyst, right, who's trying to learn the data, right? If we can make it simpler, then why not? On a graph database, again, this is going to be very simple. I'm going to add that super group node, right? So add the group with a property ID of product group, and then we're just going to link engineering sales to it. Again, no actual structure changes. All right, all we're doing, we're adding one object, and then we're gonna tie those in. And so, sure enough, if we again look at the visual descriptions here, right? you know, on the relational database, I had to add one table, 6 rows, 2 columns, and so forth. Whereas on the graph database, I just added 3 documents. And again, look how much better structured that is. We see right away what we're looking at. And that's where we get some really nice power here. And then sure enough, if we were looking at queries, I mean, now I had to even do a subquery in here, right, in order to get the data correctly. Whereas on the graph side, I had, go give me the product group, give me the out, give me the in. All right, very, very simple. All right, one more data set of changes here, management. So now we're going to add additional hierarchy. And actually, my example, Ada, the engineer, is now going to manage the sales folks, because that's how it should be. Right? The engineering should manage the sales folks. I grant you, I would also ask, why didn't you not have managers before? But at any rate, here again, now we'll create another join table, employee. I mean, again, these names might not be the most original names. I'm just doing straight naming in here, and then we'll make Ada a boss. All right, again, the query's not that hard, but I also had to do 2 subqueries in my where clause, plus a subquery in my select statement, right, just to get that data. And we end up with this again, just another table of numbers, right? And that's really the point I'm trying to make. Whereas again, on the graph side, very simple set of changes. Go find Ada, add those edges. Easy peasy, right? And sure enough, I mean, if Willis and Neil, if they both belong to another object, I actually could have made it even simpler, right? And done this in one statement instead of multiples. In the end, we get something like this, right? You see those 2 lines at the bottom, right? That's showing the new relationships. And then when I look at the query, again, now you start seeing I'm having to do a little bit more even on the graph database, but this is pretty straightforward, right? All right. So challenges, with a relational database as opposed to a graph database. Number one is the schema management, right? You notice every time we were making a change, the business rule change, we were having to make changes to our schema, right? Which required table alterations. Look, I have a very senior team that works for me, but every time that they say, "Oh, we need to make a schema change," right? We need to change this stuff around. I get a little bit worried, right? Because schema changes, they're expensive, right? They're expensive in the risk. And next, the costly writes against multiple tables, right? In relation database, we end up doing this a lot. We write to several different tables in order to have that. Now, it's good. That's good normalization, right? Which can be good when we're talking about in a relational database. But, in that graph database, I don't have to write so many different areas. We saw in the relational database, I had to do multiple joins, right? Which ended up relating to complex read queries. So, all right, so now we've seen the graph database and compare it to a relational database. Let's actually talk a little bit more about what Gremlin itself is. And sure enough, Gremlin is just one of several different vendors for graph databases. It's not actually the biggest one. Neo4j is by far the largest graph database out there. But Gremlin and Neo4j do compete very well as far as features. I would say Neo4j still has some more, but because it has more money behind it. But Gremlin is definitely, does offer some really nice stuff to it. So what is this? So Gremlin is actually part of Apache Tinkerpop, which is an open source vendor agnostic graph computing framework distributed under the commercial friendly Apache 2 license. When a data system is Tinkerpop enabled, its users are able to model their domain as a graph and analyze that graph using Gremlin graph traversal language. So it's actually called a traversal language. And then furthermore, all Tinkerpop systems integrate with one another, allowing them to easily expand their offerings as well as allowing users to choose the appropriate graph technology. So what we mean by this is, I can, I'm going to talk about Cosmos here in a moment, but I could go from Cosmos, but let's say I don't want to use Cosmos anymore for whatever reason, right? I can move it over to another Tinkerpop system because the underlying technology is all the same. So what is Tinkerpop? Tinkerpop is actually a pretty large project. There's several things that fall under this. Number one is Gremlin itself, the language that allows me to do those traversals, right, to traverse across the graph. Next, we have the Gremlin console, right? So this is an interactive shell. We're working with both local and remote graphs. Actually, it's a pretty nice little tool for doing your queries and so forth. Excuse me. Next, you have Gremlin server, right? So here, this allows hosting a graph remotely via HTTP WebSockets, right? So when we talk about Cosmos, Cosmos is implementing a Gremlin server. Next, we have the Tinker Graph. This is a small in-memory graph implementation. They're great for learning or for testing, right? Doing my unit test in memory. You have the programming interfaces, so that this is the way how we can address our code to write against this. So I do C# code. It's using one of these programming interfaces. Actually, well, it's essentially using Gremlin.net, although I end up using a couple other things in there. And sure enough, if you're curious, basically everything in Tinkerpop itself is written in Java. Then the two other pieces, they have documentation. Actually, for an open source project, they have really nice documentation, very thorough documentation. And then they have their useful recipes, right? So the idea of, I want to do a traversal that's going to look kind of like this. And they have some recipes that can kind of help you get down that path. Going a little bit deeper into Gremlin itself, and that is the logo for Gremlin. They do like that little cute looking Gremlin monster out there. But here, again, we're talking about the traversal language along with the virtual machine. It does support both OLTP and OLAP, right? So you can do that, all those different types of transactional and logical processing. But also it supports imperative and declarative querying, and it supports user-defined domain specified language, right? So so we can get to our data, in the user-defined domain model. All right, so Gremlin is awesome, but Gremlin's even better when it's in Cosmos, right? Because here I now get some real power. I mean, Gremlin provides some really nice stuff, but when I add Cosmos into it, it's great. So real quick, because I never know how much people know about Cosmos, so quickly to go through this. And number one, Cosmos is a turnkey global distribution system, right? I can literally just add data centers whenever I need them, right? Get the data as close to my users as possible, right? So at ScholarX, we have users all over the world, right? So we can easily, we can say, oh, we're getting more and more users over in India, so we can add an Indian region into there. And the thing is I literally go into the portal and click a button, and depending on how much data is in there, it might take a little while to get the data replicated for the first time. But then once it's replicated, it's kept in sync. And on top of it, I can also do multi-writes. So I can have data written in the East Coast of US and written in India, and they'll sync up to each other, right? and keep together, which is really, really nice. Next, we have the elastic scale out of storage and throughput. So sure enough, you'll never run out of storage within Azure Cosmos, because you just keep on adding more and more storage. You will pay a gigabyte for, I don't know the Australian price, but in the US, the price is a quarter of gigabytes, a quarter of $1 a gigabyte. But you theoretically will never run out of space. And then you don't really ever run out of throughput. Actually, there are some maxes, although, Azure will work with you if you really need more. But even if you really need more, the number is astronomical and also is super expensive. But, but you can get whatever throughput you need. So whether you need to handle, hundreds, thousands, millions of requests per second, across the globe, Azure Cosmos is able to handle that. And the other nice part is because the elastic scale of this, when I get those unexpected spikes, Cosmos can handle it, right, very easily. Okay, next is the guaranteed low latency at the 99th percentile. So Azure actually guarantees 10 millisecond reads and writes latency times. All right. And that, I mean, that is just amazing. On top of it, to think about it, everything in a Cosmos container is indexed. Every single property, they index everything. And yet they still can guarantee less than 10 milliseconds. I'll say, at least stateside, what I normally see, I see my reads about 3 to maybe 7 milliseconds, depending on what all I'm grabbing. And most of my writes, I will see those in about the 5 to 7 milliseconds. And again, because they're all over the world, I would pretty much expect that anywhere else as far as those type of times. Here next, we have the 5 well-defined consistency models. When I first was looking at NoSQL databases, one of the things I knew about NoSQL databases was this whole eventual consistency. And again, having grew up, right, because I mean, I started in computers back in the 70s, as far as, my father was a software developer, so I grew up in this. And, so I grew up in the SQL world, ACID transactions and everything. And I don't want to deal with those eventual consistency. This whole idea of eventually my data will be consistent. Microsoft actually, they understood that. And so they added all these other consistency models, right? So I can have strong, right? The complete opposite of eventual. Basically when I commit that data, it is guaranteed to be consistent across everything else. Now, it might take a little bit longer, right? So it'll be a little bit longer and it will cost you more. It's actually cost you twice as much in throughput, right? So there is a cost associated with that, but I do have that ability. On the two inner ends, we have bounded staleness. The whole idea of, I'm okay with a little bit of eventual consistency, but I need to know that maybe like in every 30 seconds or every 5 commits, it needs to be consistent, right? And again, those 30 and 5, you set those values, right? In the dead center is session, right? And this is the default. So this states that within a session, I'm consistent. And you think about it, that's generally what we want when we write our application. And so it makes a lot of sense as what the default is. And actually, to be honest with you, I have never done anything other than session. And I've probably done about a dozen Cosmos databases, and they've all been using the session. But then getting a little more lenient than session, but not as lenient as eventual, you have consistent prefix. And this is really interesting because in here, it's still an eventual model because eventually all your data will be consistent. But at least what you know is that it will be consistent or it'll be eventually in order, right? So, if I write A, B, and C, I know for a fact that it's going to get emitted in order of A, B, and C. Or I'm sorry, it's going to be consistent over that way, right? So it's never going to get out of order. All right, next we have the comprehensive SLAs, right? So, Microsoft guarantees 5 nines of availability. And sure enough, an SLA is really only as good as piece of paper it's written on, right? But Microsoft actually is pretty good, in my experience, of backing up their SLAs. A couple months ago, had nothing to do with Cosmos. It was actually another service that went down, but this was critical for us. And, basically a whole area of our application was down for about 7 hours. And, the support engineers that worked with us, we got it resolved. And now, like, do you want to file a claim for SLA? We're like, sure. And sure enough, and we were thinking, we're probably going to get like, $50, $50 US dollars. We actually got like $400 US dollars, right? Which kind of did a good job. I mean, it helped because we ended up having credits and actually pretty much equaled out with the credits we had to give people because of our service not being available during those periods. All right, next, it is battle tested. And what I mean by this is that you have to actually think about what Cosmos was actually built for. It wasn't actually built to be a product to be sold. They actually built it for themselves. They built it for Xbox Live, for Office 365, for Skype, for Azure itself. As a matter of fact, a lot of times when I hear people say, well, what happens if Cosmos goes down? All right. I'm like, well, are you dependent on Azure? Yes. Then you're okay. And the reason why I say that is because Cosmos is the backbone of Azure, right? So if Cosmos goes down, Azure goes down. All right. So, you're pretty good in there. Along with that, a lot of major corporations, a lot of big enterprises are using Cosmos, right? And have worked hard to make sure that this works well. kind of wrapping up on the Cosmos, what the overview of this. Number one, the ubiquitous regional presence. And what I mean, we can see the map. Let me get out of the way because I'm in the way of Australia. But it is all over the world, right? I need to count. I forgot how many regions there are now. I know they've got to be, if they haven't top 60 yet, they're really darn close to it. But I mean, and they keep on adding ones because you can actually see on this chart, they're what are they getting ready to add? They're getting ready to add in New Zealand North, right? They're adding more and more stuff on here. I did find it interesting. I was looking at these slides the other day, and apparently, at least in Australia, as long as you're on the eastern half of Australia, you're good. And on the western half, so I guess they don't need any data centers over there. I don't know, but at any rate, you can have your data being close. But on top of that, and more importantly, what we mean by this ubiquitous region presence is certain areas have requirements where data cannot leave those areas. Like here in the United States, government and Department of Defense, they actually have special regions built for those, so that their data stays private to those groups. China, right? Actually, Azure has tied in with one of the largest internet providers in China, to ensure that their data stays in the country to meet those requirements. Germany, another great example. Germany has the data sovereignty rules, right, where data is not supposed to, it's supposed to stay within the country. And again, with Azure, we can do this, and with Cosmo actually, has this built in to provide for that. And on top of it, along with everything else within Azure, it is secure by default and is enterprise ready. Grant you, by secure by default, what that does mean is that it is secure, as you buy that service. Right now, you can then go screw it up, right? But at least what what you're getting from Azure, you're going down the right path. Now, really, regardless of what type of compliance you need to meet, Azure probably already has tested against it, right? I'm on top of it for Cosmos. Data is encrypted at rest and in motion. Maverick, you don't even set those. That is by default. And you can have row level authorization. All right, and finally, the other thing to think about Cosmos, we talked a little about this, there's actually several different data models we can use, right? So we're not stuck to one different type of data model, right? So normally when people think about Cosmos, they're thinking about that one in the middle, the core or the SQL API. So a document database that allows for SQL to query those. But I can do Mongo, I can do Cassandra, I can do the table API, right? Or more probably what we care about, we can do Gremlin, right? So we can actually have these graph databases. Now, the one restriction is each Cosmos account can only do one of those data types, right? And you can't change it once you create a data account. So that is one thing you do have to consider. But that's really not as much of a limitation as it sounds like. All right, so for my last section, I want to talk about, in my couple minutes, actually, I just realized I'm going a little bit long here, but we'll quickly go through this. But let's look a little bit more at the way how the graph traversals work. So sure enough, I've been working on this test application, speaking engagement management. So like, for example, last year, I gave 40 presentations at 24 events, right? So trying to keep track of all that. And, here are basically the kind of requirements, where have I submitted to, where has it been picked up, those kind of requirements. So sure enough, here's kind of the schema that I've been working with on this. As I put that in quotes, because technically there is no schema, but in reality there is, right? Because I am actually looking at things, and you do need to think about this, especially when we talk about graph databases, because they need to understand how those relationships and the directions of those relationships. And here you can see that, all right? So real quickly to go through some of these queries, here we can see we're going in and we're grabbing all of the vertices. This is actually the query I like running with the executives when they ask, well, how much data really is there, right? I grant you, and this is actually a small set, right? Because this is just my speaking engagements. If I was to show something that has maybe 100,000, 200,000, a million documents, right? Then you really get that tight ball that kind of, is impressive. We can also query for all the edges, right? Because we can go grab those, right? But generally, or I should say, I talked about this, the schema management. This is something I highly recommend you do when you work with graph databases, is actually document your schema, your database inside the database. All right. So a lot of times, in this database, owner email address is the partition key. So it's the key that defines the partitions within Cosmos. But then you can see I have those objects. All right. And then if you look at the JSON behind there, we can see the different descriptions of all these type fields. Does a great job of defining, especially when again looking at the way how they relate to each other. Because and then some of the queries we're going to see, we have to tie those in. All right, I'm going to go through this quickly because I want to try to finish up in 5 minutes, so there's time for questions. So here's a general query. What are the presentations in my repository? You can see, again, I'll start with GV. So give me all the vertices, and then it has that property with a label of presentation. Now you might ask, why did I do this order? All right, and this is a Cosmos thing. So this owner email address happens to be the partition key. And I can do a whole presentation on partition keys. They're extremely important. This is the way how Cosmos divides up the data, so it can spread out and have unlimited data. So it is actually smart to put that first, because because it actually your database will actually search in the order that the items are given, right? And so that actually helps get more performant. And the other thing I want to point out, all my other queries, I'm not going to have that clause in there. Just assume they're there, right? Because to save space on the screen. All right, so here, so we see something like this, right? Here I can go just get the values, right? So I do .value. I can also, reason why I showed this, a lot of times, we can search for dates. A lot of times, in a NoSQL database, we want to add maybe a year, right? And go grab the year so I can actually grab things a little bit easier. All right, here we can start seeing we're going across and getting edges, right? You can see, so give me the presentation that has the name of graphing your way through the Cosmos, go to that out edge, I'll submit it to, and then will get me the inbound vertices, right? Again, I can query this again on what's confirmed, right? So get that. That's a property inside that edge, all right? So that's where we can use those properties. Again, I'm gonna go through this a little quicker because I'm gonna provide my slides. These are all of the slides. But what I did want to show, here we go. So something else you could do, you can actually query against the edges, right? Because it actually might make more sense. Maybe I have data that's in the edge, so here I want to get the edges that have the submitted to is confirmed, right? And get my inbound vertices. So, all right, I want to get to the wrapping up. So again, so there's some time for question and answers. So what did we talk about? We talked about graphs, right? So mathematical structure, a mounting set of objects in which some pairs are related. Graph theory, starts with the 7 bridges of Königsberg. Actually has a very interesting history. And then we talked about graph databases. Basically, we're taking graph theory and we're using that to represent data in a graphical way, right? Azure Cosmos DB is this globally distributed multi-model database service that provides a Gremlin database service. We looked at, I just realized this is out of order, but that's fine. We looked at graph versus relational, right? And how, in a graph database, a lot of benefits because when we work against the two. Graph traversals, right? We saw how we can actually traverse these. And again, I will provide these slides so you can see those queries a little bit more in detail. So with that, again, I apologize I had to speed up at the end. I kind of lost track of my time there. But any questions? And sure enough, definitely feel free if you'd like to come on audio and video, or you can just ask in the chat. And sure, no, if there are questions, definitely go ahead. But I definitely appreciate you all attending for the last hour. And I hope that you give graphs a chance. Take a look at them. Sure enough, you can actually create there's a 30-day trial of Cosmos, so you can actually get and it's a very large database you can create with it. And now there's actually a free database offer. So it's 5 gigabytes, 400 request units, which is the throughput you pay for. And that's going to be, it's actually interesting on the website. It shows it's free for a year. It actually is free forever. There's a reason for that. Any tools for the application layer to create graph queries. So yeah, that's actually the hardest part. Is right now if you use the SDKs as they're built, you're actually doing a lot of stream manipulation to build those. There actually was a very nice open source project, but it got abandoned and it's not even working right now. One of the things I've been working on, and I hope to have something by the end of the year, is I'm actually working on a Gremlin ORM to kind of do that. So kind of not necessarily any framework for graphs, but something that could do a lot of that type of work. But for right now, most of it is more manual. Well, great. Like I said, I'll be sticking around here for a little bit. If there any other questions come up, there is all my contact information. Definitely feel free to reach out, whether that's today, tomorrow, next week, or what have you. Right? The only caveat I always say is it might take me a day or two to respond, but I do respond to to all the emails that come out to me.